Okay, in terms of the stuff, the deadlines remain essentially the same. So exam 3, exam 4, quiz assignments part 4, deadline this Friday the 26th at 11 to 9 p.m. Also, you can look, I opened up some stuff for people who had like troubles and woes, and just open it up again for everybody. Didn't reset stuff, so if you've done it, you won't go back and say, hey, where did my scores go? But if you go back and look and you do things and you see they're still accessible, that means you can do them. It's not a trip or a trap or trick or anything. If they're available, you can do it. So you might see various quizzes and assignments still available, in addition to the ones that are obviously supposed to be available. Exam 5, the exciting final, deadline's on Wednesday of finals week at 5 p.m. And again, the way the final works is, as mentioned on other occasions, if you look at your overall grade before taking it, that's your worst case scenario. The overall grade, nothing you can do can bring the overall grade down. If you do more stuff, it either stays the same or goes up. So that'd be your worst case scenario for real. I don't have to go in and do any like adjustments or drops or anything. That is what you get if you stop doing stuff. So once you do exam 3, exam 4, all the quiz assignments which we do, look at our overall grade. If you're an A, you're done, because you can't get more A than A. If you have less than an A, then you could consider doing the final. And the way to tell if I want to do anything, thank you, is get the grade estimator and plug in your best 3 exams, plug in your overall quiz grade, overall assignment grade, look at that, and see if that would boost you up the letter grade or more. And if it can, the final could be worth taking. What happens if you don't take the final? Literally nothing, because the final is already graded as 0. So if you don't take it, nothing changes. So when the final deadline rolls around, I don't go in and like stick it in a 0, and then people go, oh my god, what happened to my grade? Where did this happen from? What happens is nothing. Literally nothing changes. So if you didn't take it and you've got like an 82.3, when grading the end rolls around, you have an 82.3. Taking it can never lower your grade because it's already at 0. You can't get more 0 than 0. So doing the final either leaves your grade exactly the same or increases it. But again, it doesn't guarantee an increase. It could be you take it, even if you get 100, it may not be enough. So if your average is like 81.3 and you get a perfect score on the final and you end up with that sweet 83.2%, still a B. So before really investing in that final, check to see if it can do anything at all. And mathematically, it's just math. You can't do it. You can't do it. There's no miracle of the finals. Or actually, I should not say there is no miracles, but no miracles are planned. The STARS quiz, the way that works is this. On Friday, I'll look upon the numbers for the STARS quiz and then put the appropriate grade in for the STARS quiz. And it's based on percentage of participation. So when you go to do the STARS survey, it's anonymous in the sense I have no idea who you are when you take it, so be honest. And it's also not just about my class, but any class you've taken in philosophy and religion. And just check class or classes you're in. I'll look at the percentage of participation, add 10 percentiles to that, and that'll be your quiz score. So if at least 80% of people do it in the class, then everyone gets a A on that quiz. The quiz can only help. It can't make your grade worse, so there's no fear about the survey. I mean, if everybody says, screw the survey, we're just not doing it, and no one does it, you just don't get points, you don't lose any points. So it can only help. And that'll go on Friday. The ABI Hardware Basic Assessment Instrument Quiz Test. If you did both of these, you'll end up, the performance on the test aren't as critical as doing them, so this will only help your grade. Also, I sent links to 2 of the assessment surveys, the Gen Ed, the one we do every year to quickly assess the Gen Ed classes. It's very short, just a few questions. And then there's also the 4-year graduation survey, also very quick. And what I'll do for that is, those are totally anonymous. What I'll do is I'll look at them, and if at least some people are doing them, this helps your grade. So maybe the case that other people doing it helps you, but they're anonymous, so I just look at, are people doing them? And if there are people doing them, then that will help you. Again, on the assessment stuff, it only helps your grade, does not hurt it. Not like a huge amount, it's not like 50 points on there, but this stuff just just helps, does not hurt. So the worst case scenario is you don't get anything, and the best case is you get some. And this will be applied after the final exam, once all the stuff's in. You won't see it on a blackboard, because they don't have a category for assessment, because that would end up scoring up what your grade looks like. So I made it like 2% or something. That would mean that if you didn't do it, you'd get nothing, and your grade would go down. So it's only a plus to your grade. And what you'll see it show up in your IRAG report. And again, the assessment can only help you. Your grade can only go up, it cannot go down. So your absolute worst case scenario is what's shown on a blackboard, and that either stays the same or goes up. It cannot, except emotional. Now the surveys, to pitch for those, you may think, oh, stupid surveys, why would I do such a thing? And of course I would kind of agree. You have lots of things to do, little time. But they're actually not BS surveys, because we have to keep our we have to address our 4-year graduation rates in order to get performance-based funding. We hit our 6-year target, then the state said, oh, you've done so well. We'll just not take that out and make it a 4-year. And so this is your chance to report to the Gen Ed Committee, General Assessment Education Committee, are there any bottleneck classes that you had trouble getting? If we get information on those, we'll work on adding more of them. Are there classes that have created other problems? Essentially, have there been any troubles for you in the Gen Ed that's bottlenecking or slowing down or impeding your graduation? So if you ever say things like, oh, I could graduate next year if it wasn't for that damn, requirement. And this is your chance to give us feedback that's listened to by the committee. We'll look at all of the stuff and we will be acting on it. So if you have any concerns about Gen Ed and graduation, they're worth doing, because it does go to the committee and we do actually look at it. Okay, so that's my sales pitch for assessment. Before pressing on to the actual critical thinking stuff, anything about any of the grades stuff? Okay. So people ask about extra credit. That's the stuff. The stars, the ABI, the assessment, that's all the extra credit built in. And again, it only helps, doesn't hurt. Yeah. Anything else? Okay, so last time we're looking at our truth functional logic stuff, and we're looking at how we do the translations. And as we saw, in this mathematical language of truth functional logic, the only stuff that we'll have in it will be variables, connectives, and parentheses. And the way to deal with this is essentially, well, one way is some people are just good at logic. They're good at math. In philosophy we call them logic hounds for some unknown reason. But they can just look at it and say, oh yeah, it's P then Q, or R, and they can just see all the stuff. If you can't see all the stuff instantly, or just want to be careful, the step-by-step approach is always swap out the English for the variables, and if the person setting up is doing their job, they'll tell you what the variables stand for. So you swap those out, and then the next thing to do is swap out the English for the connectives, and there'll always be connectives in there if it's put forth as an assignment, exam, etc. In real life, people can do all kinds of stuff. So if you're trying to do like the logical structure of, say, a politician talking, it may just be literally this, just P, Q, R, Z, just no structure at all. But when it's something that's being done for actual translation, in an exam, assignment, etc., there will be some structure to it. Say to swap in the connectives. Then the last and often the most difficult thing is putting in the parentheses, because in that case, you have to go by what the original English is saying to decide what goes with what. So like in this example, if we have P in either Q or R, it's saying you've got P, whatever that is, and either Q or R. So you can think of, to give a real life example, think of ordering like a typical, like with a sandwich or hamburger, and you have a choice of two sides. It could be hamburger and either, say, French fries or sweet potato fries. And that would be this. You get, the sandwich, and you have your choice between those two. So this is what you get, and these are the optional ones. And that would tell you where the parentheses go. Okay, so now we get to where we ended up last time, which is the test for validity. Now, validity has remained a constant concept in that the definition doesn't change, which is good. And as we saw, for argument to be valid means that if all the premises are true, then the conclusion must be true. And so what makes a valid argument valid is that putting in true premises guarantees a true conclusion. What makes it invalid is that you could have all true premises and a false conclusion. To use an analogy, like a technological analogy, software programs, or like if you're setting up an Excel spreadsheet. If you do, taking a class and you're learning how to set up Excel spreadsheets, if you have the formula set up correctly, then if you put in, suppose you're doing like a mortgage calculator, if you put in the right numbers, you're guaranteed the right result. That would be like a valid argument. Right thing in, right thing out. So you put in truth, you always get out truth. Now invalid means it's defective. You put in the correct stuff, you might luck out, get the right result. And you can imagine an Excel spreadsheet, which is sometimes, well, it can be hard to tell if you get your formulas right, because sometimes you put in the numbers and you get the right result. It seems like it's working. And the only way you know for sure is either knowing like code or putting in the proper parts and then having something clearly wrong pop out of it. And so a valid argument is one that works perfectly. Truth in, truth out. Invalid arguments, they're unreliable. Truth could go in, but truth is not guaranteed to come out. And it's important to note, and this is what often messes people up about validity and invalidity, is valid doesn't actually mean true, because you have a valid argument where everything in it is false. Because the reasoning can be perfect, but it can all be about things that are not true. To use a one fictional analogy, another class analogy, you could do like logic about the Game of Thrones, but of course all that stuff is fictional. None of those people are real, none of the things in there are real, but of course you could do logic about that. You could say like if so-and-so killed the king, then you could do all this logic and have valid arguments, but of course there is none of that. They're all just fictional characters. In the context of like a classroom, you can do word problems, etc., where everything is not real, but of course the mathematics can be good, the logic can be good. So valid doesn't mean true, invalid doesn't mean false. It means, in case of valid, if all the premises are true, the conclusion must be true. And to be invalid doesn't mean that it's false, it just means you could put it in all true and get out a false. But you might get out truth, just by luck. So how do you tell when you get a valid argument or invalid one? Well, there are many time-honored methods. One is, of course, guessing. Because if you have a deductive argument, it's 50-50. It's a coin toss. You could go heads valid, tails invalid. And you get a 50-50 shot of being right. But even with those not terrible odds, probably not the best way to do it, because you would be just guessing. A second way to do it is memorizing all the valid forms, because validity is a structural feature. So it's not what the argument is about, like being about cats or dragons or emus or squirrels. It's the logical structure. Just like a formula in mathematics. Formulas in math and physics, they work regardless of what you plug into them. Of course in physics you can put in the right stuff, but it's a matter of the structure. So if you know a valid argument form, anything with that form will also be valid. To use a metaphor, you can think of the structure of a valid argument like a plan for a house. If you have a house, where the plan is like this, here's living room, kitchen, first floor bedroom, stairs. Every house built on that plan will look exactly the same. So if you know that this is a plan of these houses, and this house is built on that plan, you would know where everything is. It always has the same plan. Now, of course, the building materials are different, but the structure of the plan is always the same. So with these arguments, they're all valid. What makes them valid is their structure, so anything with that structure will be valid. Now, there are, in theory, an infinite number of valid arguments. So you need infinite brain capacity to memorize them all. So not a great option. Same with the invalid arguments. There's an infinite number of those. So you can remember either an infinite number of valid or an infinite number of invalid. Works either way. Now, fortunately, you can get by without remembering an infinite number of them because there are some that are just very common. So if you happen to see these, you'll know they're valid. And they're so common, they get their own names. The first one is our old friend, modus ponens, also known in English as affirming the antecedent. And it's valid. So, and we've seen this time after time. First premise, if P then Q, and it's called affirming the antecedent because in a conditional antecedent consequent, here it is being affirmed, and therefore the conclusion. And my day of the week argument, like if today is Tuesday, tomorrow's Wednesday, today's Tuesday, tomorrow's Wednesday, it's got that form. So anything with that form, whether it's about days of the week, cats, squirrels, the Avengers, hamburgers, soy, tofu, whatever, it's always going to be valid if it follows that structure. Its sister argument, or cousin, or whatever relationship it might have, is modus tollens, the mode of denial, also known as denying the consequent. If P then Q, premise 1, premise 2 not Q, conclusion therefore not P. So for example, you can do a grade one. If someone gets a 70 or better, then they pass. The person did not pass, they didn't get a 70 or better. So, good logic. The third one, what's called a chain argument, sometimes called a hypothetical syllogism, because it's got two premises and one conclusion, is this. If P then Q, if Q then R, therefore P then R. Which, makes sense. If this gets you this and this gets you this, then that will get you that. So, if you have something like, if Sally studies, then she'll pass the final. If she passes the final, she gets an A in the class. Therefore, if Sally studies, she'll get an A in the class. Now, there are many, many, many other named arguments in this. This is just the three most common. For example, there's the disjunctive syllogism, P or Q, P, not P, therefore Q. There's also the dilemma, and depending on if you take another class in logic, you may see many more of these things. But they all have in common the fact that if it's valid no matter what. So again, one way to know if something's valid is recognize the form. If you recognize the form as a valid argument, and you're right, then it's got to be valid. So no matter what you put in here, again, be it about cats or tofu or backpacks or echidnas or whatever, always valid, always valid, always valid. Now, it may not always be sound, because you could put in, false stuff, but always valid. We're moving away from the three of the classic valid forms. Anything about them that needs more stuff? Now, these three good arguments have their counterparts, their evil twins, probably like Star Trek, they're mirror universe versions, evil versions. And they look like the good original, but they're not. They're invalid. Now, these get their own names because they're very common, and they get their seductive power from the fact they look like they're good, counterparts. So they look reasonable. And in many cases, they can seem perfectly sensible, and thus lure people in. But they're invalid. And since it's a matter of structure, they're always bad. Now, the danger of these things is that they do look like the good ones. So people can be taken in by them. And again, using like a sci-fi, fantasy metaphor, it's like they're doppelgangers or evil, twins masquerading as the real one, trying to trick people into accepting them. But of course, if you've seen, shows and movies where there's doppelgangers, etc., that always ends bad. They're always up to something bad. So what are the three? Well, the first one is the evil twin of affirming the antecedent, and it's affirming the consequent. If P then Q, Q therefore P. And it looks sensible, and in some cases it can seem like everything is great, like the Tallahassee soft choppy argument that I use. So this one, if Tallahassee is the capital of Florida, then it's in Florida. Totally true. Tallahassee is in Florida, totally true. Tallahassee is the capital, totally true. Seems totally reasonable. But of course it's a bad argument, not because the stuff in there is false, because whether the argument's contents are true or false has nothing to do with whether it's logically good or not. Just like if you're putting together an Excel spreadsheet or writing a program, what matters in terms of the quality of the program is the code. And whether the stuff, the information you're using is true or false is another matter. You can have a perfectly good Excel spreadsheet where you're just putting in fake numbers. It'll crunch, if it's good, it'll crunch them just fine. So the way we can tell the previous ones were good and these are bad is by our old friend the truth table. So with the modus ponens, the good one, and modus affirming the consequent, the evil one, they look very similar. But it's this switch around that makes all the difference. To use an analogy, it's kind of like think of like your car. If you take the spark plug and flip it upside down in your car, that's a time change. But if you do that, your car's not going to be going anywhere because they don't work upside down, at least as far as I know. So to see that they're valid and that one's invalid, we do our usual truth table thing. And as you might recall from the ancient days of last week, when you're building a table, you need to know the number of rows. And as we saw, it's always 2 to the n. So, and the number of variables. So in this case, 2 variables, so 4 rows. Then the columns is tricky. Every variable gets its own column, and then every premise in the conclusion gets its own column, and all the parts get their own columns until you start duplicating stuff. So there's no doubling up. So we don't, even though you get p then q, p, q, and p is a variable and q is a variable, we don't put them on there again because we already got them. And putting them on there again would just mean more work and less wasting ink or chalk. Then we got to fill in the t's and f's. So we start in the variable columns furthest to our right, alternating singles until we run out of rows. And then we head to the left, alternating pairs. And a PQ table always looks like that. It's done correctly. Then in terms of where we put stuff in our columns, the tradition is to put the negated variables close by, just for convenience sake. It's just easier. And generally the idea is you usually put like, you're going from the simplest to the most complex, just because it's easier. There's no real wrong about it, because you could actually put anything anywhere as long as you were consistent. But as a practical matter, you generally want to follow the conventions for reasons similar to wanting to follow the conventions of, say, traffic. Because if everyone doesn't know what people are doing, they're just doing whatever they want, then there can be obvious problems. So not P, that just simply negates the P column, so false, false, true, true. Not Q negates the Q column, false, true, false, true. And then P then Q is conditional, and the conditional says, hi there, I'm a conditional, look at my antecedent, look at my consequent. If my antecedent is true, and my consequent is false, I'm false. Otherwise, I'm true. So then we get to the thing we're looking for is, how do we tell when they're valid or invalid? Now, these two have exactly the same truth table, namely PQ, P then Q. What makes a difference, though, is the position they're in. Again, going back to the metaphor of the spark plug facing, right side up and right side down, it's in the same parts. You get your car, you get your spark plug. But if you flip the spark plug upside down, then things don't work as well. So for this, our good friend modus ponens, this is our conclusion, premise 1, premise 2. So, this is our premise 1, this is our conclusion, that's premise 1. So we look here, here, and here trying to find this true, and this false. And of course we never do. Now with P then Q, Q therefore P, we have the same exact table, we just look in slightly different places. Namely, this is now our conclusion, that's a premise. And we do find that we can have this being true, Q being true, and of course P being false, namely here, true, true, and false. So that shows that our modus, the bad modus, affirming the consequent, invalid. Our second evil twin, denying the antecedent. Now this one is trying to mirror or imitate the denying the consequent. So instead of if P then Q, not Q, therefore not P, it's got if P then Q, not P, therefore not Q. Now it can look kind of sensible. Like you might say, if Sally gets a 70 on the final, then Sally passes a class. Sally did not get a 70. Sally did not pass. You might think, oh, that makes perfect sense. Until you think, but wait, what if Sally got a 90 on the final? Then if Sally, she didn't get a 70, but did she certainly fail? Well, no, this could be true. If she gets a 70, then she passes. She didn't get a 70. Therefore, she did not pass. Well, that doesn't follow, because it may be true that a 70 passes, she passes with that, but the mere fact she didn't get a 70 doesn't mean she didn't pass. Again, she could have got a 70 what? Excuse me. Pixel dust, sorry. So denying the antecedent, invalid. And again, we can test this. We have our good friend P then Q, not P. And so the table would be this. And we look here for premise 1, here for premise 2, here for the conclusion. And we see we never get this true, and this false. Now the evil twin, P then Q, not Q, although it looks kind of reasonable. Again, the Sally example, if Sally gets a 70, she passes. Sally didn't get a 70, so she didn't pass. It seems sensible until you start thinking, well, what if Sally got a 71, 72, 73, up to 100? So then it kind of falls apart. And so this shakes out as invalid because the conclusion can be false when all the premises are true. Lastly, we have our evil twin of the chain argument, which is called the undistributed bill. And I mentioned back in when we were doing categorical logic, we talked about the distribution of the middle term, and you can replicate all claims with conditional claims. So, for example, all cats are mammals is logically, essentially the same as if something is a cat, then it's a mammal. So we kind of replicate the all. So if we have if P then Q, if R then Q, therefore P then R, doesn't follow. P might get you Q, R might get you Q, but it doesn't follow that if you get P, then you get R. And that would be, appealing yet invalid. For the obvious reason that just because this gets you to this, and this gets you to the same thing, it doesn't mean that this gets you to that. Now, it may seem to make sense, because if you were thinking about like driving someplace, yeah, if you can drive to a place, and you can drive to that place from somewhere else, then it would seem like, yeah, you can go there, but logically, of course, it doesn't work. So, for example, if Sally gets an 80 on the final, then she passes. If Sally gets a 90 on the final, then she passes. Therefore, if Sally gets an 80 on the final, she gets a 90, which of course would be clearly not following. So those are three super common invalid deductive arguments. Again, the evil twins of the evil mirrors of the good ones. As I mentioned before, there's an infinite number of valid arguments and a number of invalid arguments, so you wouldn't remember them all because infinite. But these are three very common valid ones, three very common invalid ones. And knowing them is worthwhile because they're, as mentioned, super common. Before pressing on, anything about those 6 that needs more stuff? So I've gone through, on various occasions, the test for validity. And again, since it's the core mission of this section, we'll go over it yet again, because there's no such thing as too much. So what we're doing in a truth table is this. Truth tables, in many ways, sound pretty cool in a way. They show a map of all possibilities. Would it sound good if you had someone like Morgan Freeman saying it in some sort of cool, big budget movie? A map of all possibilities. Also a good name potentially for a movie, possibly starring Tom Hanks looking for something. Or maybe Nicolas Cage, also looking for something. Or maybe Tom Hanks looking for Nicolas Cage, who's looking for Tom Hanks, who's fighting John Travolta. But anyways, well, I guess I'll talk to my agent about that one. So a truth table shows all possible circumstances, a map of possible realities. Now, as you might recall from what we just said, a valid argument is such that if it has all true premises, it is impossible for it to have a false conclusion. And an invalid argument is such that even if it has all true premises, it is possible to have a false conclusion. So when we're testing for validity, metaphorically speaking, we're looking into possible worlds, all of these alternative worlds, to see what could happen. And a truth table maps out all the possible worlds, given our assumptions about, any statement is either true or false, but not both. So if we can find any world, any scenario in which all the premises are true and the conclusion is false, even a single one, and it's got to be, we got to go row by row. We can't do like a connect 4 where we go this way. It has to be row. If we find even a single row with all true premises and a false conclusion, that suffices, because validity is a tough thing. Either it's perfectly valid or it's not. Even one mistake, so to speak, ruins validity forever. So in a way, it's more of a test for invalidity, because we're looking to see, is it invalid? And there's only 2 possibilities, valid, invalid. So if it's invalid, obviously valid. If it's not invalid, it's valid. Now, stripping away the metaphor, basically what we're looking to do is to see, is there, if the table is done correctly, is there a row where all the premises are true, a T under each premise column, every one of them, and an F under the conclusion column? If so, when the table is done correctly, invalid. Otherwise, if the table is done correctly, valid. Now, testing for validity, going from like kind of normal English to the table, involves the following steps. Typically what you start off with is semi-normal English. Semi-normal in the sense that I mean that if it's being done as like an exercise in a assignment or quiz or test, it generally will not be just uncivilizable garbage. There'll be like a structure in there. And not everyone, obviously not everyone talks in ways that are structured that make sense, but this will at least have something going on in there. Another example where this occurs is, of course, standardized tests. I mentioned before, the LSAT, the game section, is just a logic test, and they'll describe things in weird, English, but the idea is to translate that to symbolic form. So if anybody's considering law school, the LSAT is there to destroy your dreams, and the game section is there to really bring the destruction home. But if you know symbolic logic, you can get through that, because you'll take all the stuff they're putting out there about hats and scarves and apartments and weasels and whatever they're putting together, and you'll just put it in symbolic form and just go through the steps. So, useful skill. So we have this argument. If the Saints beat the 49ers, then the Giants will make the playoffs, but the Saints won't beat the 49ers, so the Giants will make the playoffs. So we'd symbolize it this way. If P then Q, not P, not Q. And then sort of the grinding method is you would swap out the English for the claim variables, so PQ and whatever goes in there. Then you put in the connectives, and then any parentheses that are needed. In this case, no parentheses, so super simple. Now, we've just seen this argument, so we know by looking upon it, we know it's denying the antecedent, and so we know invalid, but we can test it. So, when building the table, again, we always follow the same build process. The rows is the easiest part, always 2 to the n. So 2 variables, 4 rows. If you had 3, 8, and 16, and so on. Then we gotta put the stuff in the columns, and that's the tougher part. Every variable gets its own column, every premise gets its own column, and the conclusion gets its own column, and anything that's complicated gets broken down to parts, and all the parts get their own columns until you're down to variables, and so you can end up with all kinds of stuff. In this case, fortunately, we don't have to do much breaking down because we just have if P then Q, not P, not Q. So we put up P then Q, we get a break off P, break off Q, they go there as the variables. We have not P, not Q, and we got to break them off as well, but that's also already broken off, so done. Then, in order to do the test for validity, once you get everything in the table, much like with the categorical syllogisms, it's simply a matter of looking upon it and knowing what you're looking for. And what you're looking for is the row in which each premise has a true and the conclusion has a false. If you find that and the table is done correctly, invalid. If you don't, and it's done correctly, valid. So, premise, conclusion. So we look false, true, false. That's okay. Our conclusion is false, but one of our premises is off. So invalid means if all the premises are true, the conclusion could be false. But premise is false, so okay so far. Then we have false premise, true conclusion, also okay. But here, true premise, false conclusion, so invalid by definition. Now we could just stop there because once you find the all true premise and a false conclusion, you're done. But to use an analogy, it's kind of like if you're checking out a water bottle to see if should I bring this to class or go biking or whatever, and you find like a big hole in it. Well, you don't have to keep looking for more holes, because at that point it's like, well, yeah, that's done. You may have more holes in it, but once you have one big hole in your water bottle, you're not going to be using it. Like similar idea here. There may be more bad rows, but once you find one, it's done. The last one, of course, is fine, but again, it's like having a water bottle. You got a big hole in the bottom. The rest of it may be okay, but the bottle is, at that point, useless. It's not going to hold water. So not surprisingly, this checks out as invalid. Before pressing on to our next exciting slide, anything about that? It needs more stuff. Another example. The argument is we're going to have a large mass of Arctic air, that'll be our A, flowing to the Midwest unless the jet stream, J, moves south. Unfortunately, there's no chance of the jet stream going south. So you can bet there'll be Arctic air flowing to the Midwest. So symbolized, we get A or J, not J, A. And this also shows that you can, if you're consistent, you can kind of break the conventions. Normally it's P, Q, and R, but you can use whatever variable you want as long as you're consistent. In fact, if you were artistic, you could use like little cartoons as long as you were consistent about it. This could be like, a cartoon of Garfield, a cartoon of, Batman, Deadpool, or whatever you want. As long as your symbols are consistent, that's fine. So we build our table the normal way. We look to see the parts we got, how many variables we got, 2 variables, so 2 to the n, so 4 as always, in this case. Then we build the columns. Each variable gets its own column. Premises get their own columns. Conclusion gets its own column. It's simple arguments, so we don't have to break anything down any further, so we get all this stuff. And then it's just a matter of looking upon it to look for ultra premise and a false conclusion. If we find it, invalid. If we don't, valid. So premise, premise, conclusion. So, if we were like in a super hurry, we can ignore these first two rows because the only rows that matter are rows in which the conclusion is false. Because the only thing they can show an argument being valid is a false conclusion. So these rows are effectively irrelevant. So these are the ones that matter. Of course, by talking about it, essentially made it kind of matter. So we go to here, we have a false premise, a true premise, a false conclusion, but that's okay, because valid means if all the premises are true, the conclusion must be true. Invalid is you could have all true premises and a false conclusion. So it's okay to have false premises because they don't show it to be invalid. Lastly, true premise, false conclusion. Also okay. So we built the table correctly, went through row by row. We didn't find a single row in which all the premises are true, and the conclusion is false, so it's valid, which is good. Because you might recall from some time ago, this is actually disjunctive syllogism, which is another standard valid argument. So A or J, not J, A. So valid. And of course this can be done with anything that's fits into true functional logic. It's just a matter of getting into symbolic form, building the table, checking the table. Now what about bigger table? Now with bigger table, it just means more stuff. It's a difference in not in kind, but a difference in basically volume. There's more stuff there. Now some things, making it bigger does kind of change how it works. For example, recipes don't always scale up perfectly. So sometimes if you've ever made stuff and we're scaling it up, it may not always work perfectly to just like double the ingredients. Sometimes it doesn't always work out. Or like with running, you could look at a marathon as a whole bunch of quarter miles. But if someone can run like a really fast, say sub-minute quarter mile, it obviously doesn't mean they can keep doing that for 26.2 miles, over and over again. Maybe they can, but it's more than just running a bunch of quarters. Now, fortunately, with the truth tables, it does scale perfectly. Doing a bigger one changes nothing except it's bigger. Now, it does create some practical problems, namely, it gets obviously increasingly boring, and the more stuff you get going on here, the more likely it is just by chance or boredom or intention that something will end up in the wrong place. Especially true back when, back in the day, everything was done by hand. You're trying to do truth tables by hand and line everything up. And when I used to write them out on the board, I remember I'd have to go back and make sure I had them all lined up properly because I'm trying to freehand draw them. But fortunately with the power of PowerPoint, no problems anymore there. So what happens if you end up with like a 3-variable table? Now the 3-variable table is just one step up. Because of the formula r equals 2 to the n, you get a really big increase every time you add a variable. So it jumps from 4 to 8, to 16, 32, 64, etc. And at you can see already at this point it's not quite ridiculous, but pretty close. And as you might imagine, a 16 row table would be a lot of paper for pixels. But the same process always works the same way. So you get the argument. If Scarlett is guilty of the crime, then Miss White must have left the back door unlocked, and the colonel must have retired before 10 o'clock. However, either Miss White did not leave the back door unlocked, or the colonel did not retire before 10. Therefore, Scarlett is not guilty of the crime. So when doing the translation, what you get is what the variables stand for. In this case, S is Scarlett is guilty, and it's important to watch for what's in the variable, because even though kind of the normal thing to do would be that the variable would be a positive thing, and then you negate it. So if you want to say that she's not guilty, you'd say S is Scarlett is guilty, and to say she's not guilty would be not S. But people sometimes put the negative in there. So someone might have S being, she's not guilty, in which case not S would be, she is guilty. And so you'd always want to watch for, what's going to the variable. So although generally you shouldn't do that because it gets confusing, you can put negatives and just stuff them into the variable. But as long as you're consistent, it does works out fine because the true functional stuff. And W is Miss White left the back door unlocked, and C is the colonel retired before 10 o'clock. So we end up with S, then W, and C, and of course one of the challenges is where the parentheses go. But we know from the wording that if she's guilty, we know that both of those must have happened. So this entails both of those. Then we have W didn't happen, or C didn't happen, not W or not C, and we have not S as our conclusion. Now, building the table here, as you might imagine, becomes somewhat more complicated, because now we got not only more rows than usual, we also get a lot of columns going on. Now, fortunately, the row is always easy. There's a fixed formula, 2 to the n. So we have 3 variables, so we end up with 8 rows. Then, the columns is always the kind of messy part. Unfortunately, there's not like a nice formula like C equals, 3 to, B, none of that. What C equals is the number of variables, number of premises, well, of course 1 for the conclusion, then all the stuff that's broken down, and so there's, you could write this all out, but it's essentially just, every variable, one for the conclusion, 1 for each premise, then breaking down all the premises and possibly the conclusion into their simplest parts, until you get down to variables, and that all goes in the column. So there's not like a nice simple formula for that. It does have a consistent way of working, but again, there's no really handy formula. So what we have to do is take our stuff and break stuff. So here goes the breaking of the stuff. So we have one premise gets a column. Other premise gets a column. Conclusion gets a column. If we just did that, then of course we couldn't do the table because we just have that stuff. We wouldn't be able to fill in the T's and F's. Now, if you're logic hound, you just know how to do it. You can just fill them in just from that because you just grasp the tables. But if you don't have the workings of logic all memorized perfectly, you need the rest of the stuff to fill in the stuff. So what other stuff has to go up there? Well, what we have to do is, again, each premise and the conclusion get their own space. Each of the variables, of course, gets their own space, so those go there. That's the easy part. But then with these things, you got to break down the parts. Anytime you get parentheses, etc., more stuff going on, you got to simplify them down to the variables. So anything that's not just a variable has to always be broken down until you have, kind of at the bottom of the breaking, just the variables. And every part that's broken off gets its own column. So each premise and conclusion gets its own column. Then as you simplify them step by step, each of the parts that make them up, until you get down to the claimed variables, gets their own column. So it can be kind of messy. So this gets a column, then we have to break it into its parts. So breaking this apart, we have S, and we also have W and C. That breaks down to those. So S gets a column, W and C gets a column. But then of course we got to break down W and C. This all breaks down to S, W, C. And we got those there. So S, W, and C. So column for this, column for the S, column for the W and C, column for W, column for C. So that generates by itself 2, 3, 4, 5 columns just off from that. This will be slightly simpler because we have not W or not C. So we have W, not C. So this gets a column, this gets a column, this gets a column, and then of course you gotta break these down, so those get a column. So this generates 1, 2, 3, 4, 5 columns. Now there aren't any repeats, so you don't, we have W and C here, W and C here, and as you can see from the table, we don't keep adding on the same thing. Could you do that? You could, but it would just be wasting time and pixels or ink. You'd just be doing the same thing, over and over again. The not S, it's got to be broken down, but this just breaks down to S. But we already got it, S already up there, so we don't, again, we never double them. So from those three things, we get all these columns. And again, in terms of why we need to break stuff down, is because we can't do the truth value of these things until we get the truth values of the parts. So to get the truth value of this, we need the truth value of S, and we need the truth value of W and C. To get the truth value of W and C, we need the truth value of W and also C. And similar for this one, to get the truth value for not W and not C, or not C, we need the truth value of not W, we need the truth value of not C, which requires us to get the truth value of W and the truth value of C. So that's why we need all the parts out there, because to know the truth of the whole, you gotta know the truth of the parts. Hence, all the breaking down of things. Huh. So then we put the table together. Now again, the number of rows is easy, always to the end. So in this case, 3 variables, 8 rows. Then for the columns, which is what we're just working on, everything's got to get a place. So the variables always get their place over furthest to the left, and then we put in the rest of the stuff. The premises, the conclusion, and then the breakdown of the premises to conclusion. So from this, we end up with all this stuff. So then, once you have the table in place, it's just a matter of, well, basically grinding. You're doing, it's a very repetitive task. But as long as you do each step correctly and avoid, stay focused, which is why logic accountants drink a lot of coffee, I would suppose, is you've got to do each step correctly. But as long as you do each step correctly, then the whole thing works out because it's true functional. So, as always, we start off furthest to our right, alternating singles. So true, false, until we run out of rows. Then we head to the left, alternating pairs until we run out of rows, and then heading to the last column, alternating groups of 4. So the rightmost variable column, if it's done correctly, is singles, TF, all the way down. The leftmost is always half and half true, half false. And so if you want to save, shave off like a tiny amount of time, you can just do the first and last columns of the variables that way. They'll always be half and half and singles. Then it's filling in the rest of these stuff. So we have the not W, and that's a negation. Now, our example of negation, going back to the beginning of this, was of course negating P. P, if it's true, becomes false, false becomes true. So in this case, what negation does is what it always does. It says, hi there, I'm negation. If what I'm negating is true, I'm false. If it's false, I'm true. So essentially we take the W column and we reverse the polarity. So W is true, true, false, false, true, true, false, false, and not W just reverses that. It becomes false, false, true, true, false, false, true, true. Not C is just the negation of C. So you take the C column, and again you negate it. So true, false, all the way down becomes false, true, all the way down. Then we get the W and C, and it's a conjunction. So as long as you know what the symbols mean, you can always, as long as you grind through each step correctly, the whole always works. It's, by its very nature, is true functional. If every step is done correctly, the whole thing always works. So this is W and C. So you look here and here, and a conjunction says, of course, I'm a conjunction. If both my conjuncts are true, I'm true. If either one of them or both are false, I'm false. So it works just like in normal English and. If you're having a party and someone promises, they swear they're bringing hot dogs and rolls, the way they told the truth is if they show up with hot dogs and rolls. If they showed up with just hot dogs, they lied. If they show up with just rolls, they lied. If they showed up with nothing, they double lied. So we look to these two columns. So when they're both true, it's true. When one or both are false, it's false. So it's true, false, 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 true, false, false, false. Then we hop here. So this is a conditional. Now, as I mentioned before, when you have stuff in parentheses, you can treat that literally like a container. Going back to my grocery store analogy, if there's like a checkout lane, 10 items or less, and you're a stickler about the rules, if you have, say, box of cereal, you have one item, you don't have thousands, even though there are like thousands of like flakes or whatever in there. Or if you have, a bag of oranges, again, that would still be just one item. Even though there would be 10 oranges in there, it'd still just be one thing. And so you can think of these as being kind of like in a box or a bag or a bucket, or a shipping container, or whatever metaphor you'd like. And so S and W and C, this is the antecedent, and W and C is the consequent. So what we're doing is we're looking at this column for our antecedent to this column for consequent. And a conditional always says, hold on, I'm a conditional. Look at my antecedent. If that is true and my consequent is false, I'm false. Otherwise, I'm true. So what we're looking for is true antecedent, false consequent. Otherwise, it's true. So anywhere where the antecedent is false, we can always put it in as true. So these bottom ones, we don't even have to look at W and C. So if you want to shave off like milliseconds, you could say, oh, the antecedent is false in these four columns. If you have false antecedent, conditional is always true. So then here, true antecedent, true consequent, true. True antecedent, false consequent, false. True antecedent, false consequent, false. True antecedent, false consequent, false. And so we end up with this: true, false, 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 true, 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 true. Then the grind continues. So not W or not C. Now, even though there's negations in here, the negation, you can think of it as like something stuck onto something else. To deal with the grocery store metaphor, once in a while you can buy something and it has like something else stuck to it for free. For example, like, I haven't seen this in a long time. I remember sometimes you get a special where you buy the toothpaste and there's a toothbrush, hopefully in a container, glued to its side. And you get the, it says like free toothbrush. And if you're going through the 10 items or less, that's one item, not two, because it's like stuck on there. So the conditional, the negation is stuck onto there. So we treat it as one thing. So not W or not C. So what we look at is the not W column, and we also look at the not C column. And this is a disjunction which says, hi there, I'm a disjunction. If either of my disjuncts are true, I'm true. If they're both false, I'm false. And again, this corresponds to the inclusive or normal English. So if someone says they're bringing, you're having a party, and someone's in charge of like dessert, and they say, oh, I'll bring cake or pie, they've told the truth, they show up with cake. They told the truth, they show up with pie. They told the truth, they show up with both cake and pie. The only way they've lied if there's no pie and no cake. So we look to these two columns, and it's true except when they're both false. So false or false is false. False or true is true. True or false is true. True or true is true. False or false is false. False or true is true. True or false is true. And true or true is true. So that. And then finally, the not S column. Now, negation, again, always does the same thing. Namely, it inverts, reverses the polarity. So we take our S column, which is true, 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 false, 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 and we just invert it. It becomes false, 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 true, 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 true. So after all that, it just comes down to looking upon the table. Now, as mentioned before, you can shave off, milliseconds. It's not like a huge statement, you can show off some time, because for the test for validity, or invalidity if you prefer, the only rows that matter are the ones where the conclusion is false. If the conclusion is true, it can't tell you whether it's valid or invalid, because what we're looking for is all true premises, false conclusion. So the critical rows are always the rows where the conclusion is false. So we can effectively, again, to save milliseconds of time, we can ignore the bottom four there. So what we do is we look at our premise 1, premise 2 conclusion. And what we're trying to do is see, can this be true and this false? If we find that, invalid. If we don't, valid. So we check here, true premise, false conclusion. But that's okay because even though the conclusion is false, we have a false premise, so it's okay. False premise, true premise, false conclusion, again, still okay. We do have a false conclusion, but not all our premises are true. Then false premise, true premise, false conclusion, also okay because, again, they're not all true. Then finally, false premise, true premise, false conclusion, also okay because we don't find both of these being true and the conclusion false at the same time. And again, if we were being like really tediously thorough, we'd keep on checking row by row, but at this point it'd be pointless because here the conclusion is true in these 4 rows and it can't show it to be invalid. So again, if you want to shave off milliseconds, you only need the rows where the conclusion is false, because they're the only rows that matter for that. And so we don't find the possibility for this being true, and that being false, and so the argument is valid. Now looking at it, one thing you can note is it actually has the structure very similar to a modus tollens. It's if S, then W and C, and this effectively is the, it's not W or not C, kind of the negation. So it's not terribly surprising that it turns out to be valid, because it's very similar to modus tollens. So that would be a 3-variable grind of a table. And of course they can get bigger. Again, theoretically they could be infinite, but you couldn't do them because they would require infinite time, unless you could do things instantaneously. As a practical matter, unless the professor is a psychopath, which is not unheard of, they generally wouldn't have you do anything bigger than a 3-variable table, because beyond that, as you can see, it starts getting more ridiculous. Before going to our last bit, namely the short method, anything about the normal method that needs more stuff. Okay. Now, as I mentioned, said repeatedly, the only rows that matter are the rows where the conclusion is false. And I spoke of saving milliseconds on this. Well, there's a way to save even more time, potentially. It's what's called the short truth table method. Now, like many shortcuts, it has the risk of turning into a long cut. Namely, you may find that trying to use it as a practical matter ends up taking you way more time than doing just the truth table. Because doing it quickly to make it into a real time saver, you would generally have to know how to do tables really, really well. Because it does require knowing how all this stuff works. So as a practical matter, it may turn out like many shortcuts, it ends up taking way longer. So you have to, again, if time is of the essence, you'd have to kind of judge, is the shortcut really a shortcut, or will it take me 10 times as long? So how do you do the short method? Well, it rests on the idea that, as we've seen, if an argument is invalid, that means there must be at least one row, possibly more, in which all the premises are true and the conclusion false. So, what you can do is try to skip all the other parts and only focus on building one row. So again, there'll always be, if it's invalid, there'll always be a row that shows it to be invalid. You just need one. So if you can build that row, it's invalid. If you can't build that row, it's valid. So what you try to do is basically force a false conclusion in all true premises. And if you can't do it, you're doing it correctly, valid. If you can, invalid. Now, this is where the shortcut can become a long cut, because in some cases, neither the premises nor the conclusion will force a definite assignment of being true or false. So what you'll have to do is essentially grind through it. So here's how you do it as an example. Again, the theory behind it is that all you need is one row in which all the premises are true and the conclusion is false. So you're trying to create that row. Basically, you ignore all the other rows and you try to build that one row that does the trick. If you can do it, invalid. If you can't, valid. And again, the problem with it is, it's a practical matter, trying to do that may take you way longer than doing the table. So it becomes a judgment call. How fast can I do this with a short method? Will it take me much longer? If it does, then the whole point of it is lost. So we take this, P then Q, not Q then R, not P then R. Now we could, of course, just build a big table for it. Take time, but if we do it correctly, we get it right. Or we can do the short method. So what we have to do is this. We have to make this true, make this true, and make this false. So that's what we try to do. So we still write out our columns. So we don't avoid the column grind. We have to figure out, okay, we've got this gets a column, this gets a column, this gets a column. Then the variables get their columns. The not Q and not P get their columns. So we've got all that stuff. We still have to do all that column stuff. The only thing it saves is you're not putting in every single row. And as you can see already, you're doing most of the work anyway. So what some people just say, this is kind of pointless, but here we go. Now we need to make the conclusion false, not P then R. So for this to be false, we need a true antecedent and a false conclusion. So not P has got to be true, which means P has to be false to make that true. R has got to be false, so there we go. Now if we assume P is false, P then Q is true when Q is either true or false. So this doesn't force an assignment for P then Q. It could be true, it could be false. So what we have to do is we have to keep going because we don't know what to put in there yet. There's obviously two possibilities. Now if we assume R is false, not Q then R is true when not Q is false. Because again, a conditional is false when the antecedent is true and the consequent is false. We've already established R is false for that row, so not Q must be true. So we must assume, in this case, Q is true to get that true. So we got to assume this is going to be, this instance is false, we're going to make this false. So to get that being true, not Q is false, so Q must be assumed to be true. So that way we get all our variables assigned. P in this row is false, Q is true, R is false, P then Q is true, not Q is false, not Q then R is true, not P is true, not P then R is false, P is false. And so we end up with all true premise and a false conclusion. And maybe that took slightly less than doing the whole table, but it did save some ink. So I guess it is an environmental, it's more green, I suppose. So the short truth table method is an option, but again, it's a pragmatic judgment call. Can I do the table faster with the short method, assuming I don't have to show my work? If you have to show all your work anyways, then the short table is irrelevant. But if the thing is just, I need to know whether it's valid or invalid, the short table could save time. But again, it's a pragmatic matter. Can I grind through this quicker than doing the table, and is it worth doing so? Okay, so that's the short truth table method. Next time, we'll head on to basically a review of the stuff in anticipation of the final, etc., and then wrap all the stuff up. So be sure to complete, if you haven't done so already, exam 3 and 4, because assignments part 4, April 26th. If you need the final, again, the way to tell if you need it is look at your overall grade. If your overall grade is an A, you're done. You can't get more A than A. If it's less than an A, you can get the grade estimator if you think, if you're interested in taking the final, and plug in, your best 3 exams, plug in your overall quiz grade, overall assignment grade, hypothetical 100 for the final, and see that overall grade. If it's a letter grade or better, the final can be worth it. If it changes nothing mathematically, there is no like secret miracle of the final. If it can't do anything, it can't do anything. But keep in mind there's going to be the STARS extra credit, set announcement of that. There's also the argument basic assessment instrument, the post test, and the assessment surveys. As mentioned before, these only help. Your grade can never go down. It only at worst stays the same or goes up. And I'll apply these after the final exam, and they don't go on Blackboard because if I put a column for it on Blackboard, it would knock your grade down, which would screw things up. So I do this manually at the end. So you won't see this until the end. And if you have questions about that, just email me and I'll post more announcements and etc. So good rest of the day, and I'll see you on the Thursday.